Today, inshallah, we are going to start the acid-base titrations, pH curves, and indicators. Of course, as I told you from the beginning of this chapter, that this chapter is very, very important. Its questions, its problems, they are very, very important. Of course, we're going to see how to solve the problems because the problems would need us to practice a lot in order to know how to be perfect in solving its questions and its problems. So we are going to take the acid-base titrations, pH curves, and indicators. Now, of course, we studied titration before in O-level, and we've seen that titrations means that if you have, for example, an acid that is with unknown concentration, you do not know its concentration, and you want to find out its concentration. Hello, Yazulfa. So you make something called titration using something that is opposite to it. So if you have an acid with unknown concentration, so if the acid is the one is with unknown concentration and you want to determine the concentration of this acid, so you titrate it with something called a base, which is opposite to the acid, that has a known concentration. And of course, by titration, we use the apparatus where we take one of them using a pipette. For example, if you take the acid, for example, take 20 centimeter cube of the acid using a pipette, because in titrations, all the volumes must be very, very accurate. So you cannot take the volumes using a measuring cylinder. You have to use either a pipette or a burette. And taking whatever is going to be placed in the conical flask, we use a pipette, and we are going to place, for example, the acid here in the conical flask, and then we are going to fill a burette using the other solution with known concentration. It doesn't matter whether you place this in the conical flask or the other, it doesn't matter, but one of them is placed in the conical flask and you place the other in, for example, here you place the base of known concentration, you place it here in the burette. And then since the acid and the base, both of them are colorless, we have to add here an indicator. And as we know from our definition that the indicator is something or is a substance, it's usually, mainly it is a weak acid, sometimes it's a weak base. So the indicator is a weak acid or a weak base that changes its color in presence of the acid medium than it is in the alkaline medium. So here we have, for example, an acid with an unknown concentration. So we take 20 centimeter cube using a pipette and we place it in the conical flask, and we place the base with the known concentration in the burette. As I told you, it doesn't matter. You can place the base even if it is the one with the known concentration. We can place it in the conical flask and the acid in the burette. It doesn't matter. But because both of them are colorless, then we have to add an indicator, and the indicator is a substance, usually a weak acid, that will change its color. It has different colors. Hello, Ya Wafa. It has different colors in the acid and in the alkaline medium. So what happens is that, of course, up till now, we only took two indicators, the methyl orange and the phenolphthalein. I'm just reminding you that we have two indicators that we already studied, but now in this chapter, you will see that we have a lot of indicators, not only the two that we took in O-level. We have an indicator that is called phenolphthalein indicator, and we have another one that is called methyl orange indicator. And we see that the phenolphthalein in the acid medium has a colorless color. It doesn't have any color. In the alkaline medium, it has a pink color. It has no intermediate color in the neutral medium. It has, yani, there is no specific color for the phenolphthalein in the neutral medium. It's either colorless in the acidic or pink in the alkaline medium, but has no third color, whereas the methyl orange has a red color in the acid medium, has a yellow color in the alkaline medium, but has an orange color in the neutral medium. As I told you, these are two examples of indicators, but in this chapter, you will see that we have many, many indicators. And even what they wrote here in in your syllabus is not all the indicators that we can have. We can have more, of course. Now, we titrate. It means that we add, when we say titration, it means addition of whatever is present in the burette. We add it drop by drop to whatever is added in the conical flask until what? Because both of them are colorless, so we cannot see any change happening when we add the base to the acid. We will not see any change because both are colorless. But when we add an indicator, so for example, when we use, for example, methyl orange, I'm going to write it MO, methyl orange, phenolphthalein, pH. So if we are placing methyl orange here with the acid, then its color is going to be red, and we are going to titrate using the base until the color of the indicator changes from the red color to the orange color. So we close the tap and we see the volume of the base that is required to neutralize the 20 centimeter cube of the acid. Hello, yes, Sarah. Okay, so this is what we call titration. Titration means that we add a base to the acid. Hello, yes, Sarah, how are you? So titration means that we are going to add a base with known concentration, for example, to the acid with the unknown concentration that we want to determine. By the addition of an indicator, the indicator will show us when the reaction stopped, when all the acid in the conical flask has completely reacted or completely neutralized with the base that we are adding from the burette. And so when the color of the indicator changes, this will show us that all the acid that is present in the conical flask has completely neutralized by the base. So we call when the color change, when the color of the indicator changes, we call this the end point. So we have a definition that we are going to see here, that we have something called the end point. We are going to use this. The end point is, it is when the indicator yes, okay, it's okay, Asad. So the end point is when the indicator changes. It is when the indicator changes its color during the titration. You're welcome. When the indicator changes its color, we call this the endpoint. But we have another definition that is called the equivalence point. Here we have, let me write it in a different color. We have here what we call the equivalence. The equivalence point. The equivalence point, we say that it is when the acid, is completely neutralized by a base or an alkali. Okay, which is completely, it is when the acid is completely neutralized by a base, depending, of course, on their stoichiometry, as deduced by their stoichiometry. Stoichiometry, it means how many moles react of the acid with how many moles of the base. So we have to differentiate between the endpoint is when the color of the indicator changes during the titration. We call this the endpoint. We say add the base until you reach the endpoint. Until you reach the endpoint means when the color of the indicator changes. So this is called endpoint. And we have another definition, which is called the equivalence point. It is when the acid is completely neutralized by a base as deduced from their stoichiometry. As we are going to see that these 2 points nearly coincide. Nearly they are the same. That's why sometimes when we refer to equivalence points, sometimes we say the endpoint, although there is a little bit difference as we are going to see now. Yani the endpoint is when the indicator changes its color, but the equivalence point is where the volume of the base that is added to completely neutralize the volume of the acid depending on their stoichiometry. Okay, so today, inshallah, we are going to see how can we choose our indicators, because sometimes you have you are reacting, for example, HCl with sodium hydroxide. Sometimes you are reacting ethanoic acid with sodium hydroxide, as we have seen previously that HCl is a strong acid and ethanoic acid is a weak acid. So when we titrate a strong acid with a base and when we titrate a weak acid with a base, this will differ on choosing the indicator that we are going to use. We are going to see that the indicator is different when I want to make a titration between a strong acid and a base or a weak acid and a base, then the indicator could differ. And also, if you are titrating a weak, for example, a weak base with an acid or a strong base with an acid, also the indicator could differ. So today we want to see which indicators, as I told you, there are no, these are not the only indicators that we have. So today we want to see what we call the pH curves, and from which, how to determine which indicators to be used. That's what we are going to see today. What are pH curves and how to choose the indicators in any titration. So do you have any question concerning titrations before we proceed? Okay, so what are pH curves? The pH curves, we are going to draw them. They are plots between, these are plots between the pH of the solution with the volume added, from the burette. Okay, so we are going to use, in order to measure the pH of a solution, we are going to use what we call a pH meter. So we are going to use a pH meter. I'm going to show it to you in the book. So in order to plot the pH curves, which means plotting the pH of the solutions against the volume added from the burette, then we are going to use something called a pH meter. And as I told you, we want to make this titration without using the indicator, so that to know which indicators are we going to use. If you are titrating ethanoic acid with sodium hydroxide, can you use both indicators, phenolphthalein and methyl orange both? Can you use any other indicator? So this means that here we are not going, whatever we are going to do now is to make a titration between the acid and the base, but not in presence of the indicator. We want to know which indicator are we going to use. So instead of using the indicator, we are going to use what we call a pH meter. So you will see that here, in order to draw these plots, this is the pH meter that we are going to use, as you see here. Instead of using the conical flask, we are not going to use the conical flask. We are going to use a beaker, for example, and we place a specific volume, and this volume should be accurate. As I told you, all these calculations here should use accurate volumes. So we are going to place an accurate volume of, for example, a base. And here we are going to use the pH meter. This is the pH meter that we are going to use This is called a pH meter. As you see that it is an apparatus where it has a screen and it has what we call a probe, or sometimes we call it an electrode. This is a probe or electrode. You can call it an electrode. It is a glass electrode. As you see, it is made of glass and it is connected, the pH meter is connected to this electrode. We place the electrode in the beaker containing our solution. At once, you will see that there are numbers here, and these numbers are the pH of the solution that we are dealing with. So here it is clear that since the pH here is 3.2, this means that this is an acid. They placed an acid and they placed the electrode, and at once, as soon as we place the electrode of the pH meter in the solution, at once it will read the pH. Now, as we said before, that the pH is minus log the hydrogen ion concentration. Now, what we are going to do is to get a burette, and we are going to drop, if this is an acid, then we are going to drop a base from the burette, or of course the opposite. If we have a base, we are going to add an acid from the burette. So that's what we are going to do to measure what happens as more and more of the acid, or as more and more of the base is added from the burette, what happens to the value of the pH. So let's take the first titration that we are going to do is the titration of a strong acid, with a strong base. For example, we have a strong acid like HCl. We have a strong base like sodium hydroxide. So if we start here using our beaker, if we start here using the beaker and we add here 25 centimeter cube, if we add 25 centimeter cube of 1 mole per decimeter cube of sodium hydroxide, for example, using a pipette, of course, and we are going to place here in the burette. We must use a strong acid like HCl. So we are going to use a burette and fill it with HCl of the same concentration, which is 1 mole per decimeter cube. Here we know both concentrations, and here we are not dealing with how can we determine the concentration of one of them. No, here we know the concentration of both, but we want to determine which indicator to be used. So here we are going to get our pH meter, which has the screen containing the numbers, and connected to it will be the probe or the electrode that is going to measure what happens during the titration. As we add more and more of HCl to the sodium hydroxide, what will happen? And this is what we call the pH curve. Now, to draw the pH curve, we are going to draw the pH against the volume of HCl added from the burette. I'm going to write it a little bit here. The volume of HCl added from the burette. So before addition of any drops of HCl, we have the sodium hydroxide, and we know the sodium hydroxide is a strong base. So Yassine, what will be the pH of sodium hydroxide as it is a strong base? Yes, Yassine. If you have sodium hydroxide, a strong base, what will be the pH of sodium hydroxide?
Miss, I'm not sure.
Why? Why you're not sure? Yani you took this in O level, you took it in AS, and I gave it to you the 2 previous lessons. So how can you not know that if you have a strong base, what will be its pH? يعني it's يعني approximate pH. Yes يا أرنا, excellent. وفاء, excellent. Yes يا يوسف, يا ياسين.
Miss, if it's a strong base,
Yes.
it will be above
Yes.
7 and below 10.
Okay, if it is strong, we've taken this a lot. يعني, as I told you in O level in AS, and even I repeated this in the previous 2 lessons. يعني, if you have 7, this is neutral. From 0 to 7, this is acidic, right? And from 7 to 14, this is basic. The more you approach the 0, this means that you are having a strong acid. If you have a strong acid, its pH is from 0 to 2. If you have a weak acid, its pH will be between 3 and 5. You have to know all these things. They are going to ask you to draw plots of what I'm going to say now. They are going to ask you to make calculations. Yani, this chapter needs you to be very attentive while I'm explaining, and very attentive when we solve questions. It's very important. This chapter does not depend that you take rules or you take basics and you have to know it and that's all. No, you have to use your mind. You have to work. You have to see how to solve problems, how to draw titration curves. That's what they are asking you in this chapter. If you are having a base, it starts from the 7. Whatever is near to the 7 means it's a weak acid or it is a weak base because it is near to the neutral. But as the pH goes higher, this means that as you go to the 14, it's a stronger base. Stronger base. So the more we approach the 0, the stronger is the acid, and the more we approach the base, the more we approach the 14 is a stronger base. So if you have something like sodium hydroxide, as we know from O level that it is a strong base, then this means that its pH will be between 12 till 14. The pH is about from 12 to 14. But because we are using 1 mole per decimeter cube, this means that the pH that we are going to start with is the 17. Yani, you place 25 centimeter cube of sodium hydroxide having this concentration. This concentration is considered a high concentration. If you say 0.1, then this means that it's a lower concentration. 0.01, much lower. But 1 is a high concentration. And that's why its pH will be about 14. You started with 14. The pH starts from 0, 7 till 14. So you are starting with the 14 because we started with sodium hydroxide. You have to know from where are you going to start the titration curve. Since we placed sodium hydroxide in the beaker and sodium hydroxide is a strong base, this means that we are going to start with the pH 14. Okay? Type. Now, what happens when HCl is added to the sodium hydroxide? Will the pH change or not? Now, before we deal with this pH will change or not, if you are having the HCl and sodium hydroxide, both of them have the same concentrations. And since when we write the equation between the reaction between HCl and sodium hydroxide to give sodium chloride and water, so we know that if the concentrations are the same, and since the mole ratio is also the same, this means that, yes, Sarah, this is neutralization. That's what I'm explaining. This is neutralization. Neutralization means an acid is reacting with a base to be neutralized. Okay, so if you are having the reaction HCl plus sodium hydroxide giving sodium chloride and water, and since the mole ratio here is 1:1, and since both of them have the same concentration, so what do you expect the volume of HCl that is required to neutralize the 25 centimeter cube of sodium hydroxide? What do you think, Arna? Shall I repeat my question? If you are titrating HCl with sodium hydroxide, and we know from this equation that HCl and sodium hydroxide react together in a mole ratio of 1:1. So if the concentration of both is the same, and we used 25 centimeter cube of sodium hydroxide, what would be the volume of HCl that will neutralize the sodium hydroxide? Yes, ya Wafa.
Also 25 centimeter cube.
Excellent. Excellent, ya Arna. It should be also 25 centimeter cube. So we know that since both of them have the same concentration, both of them have the same number of moles, and we know from O level and AS that the number of moles is equal to the concentration times the volume. So if they have the same number of moles, they have the same number of moles, and they have the same concentration, this means that the volume should be equal, which means that there should be 25 centimeter cube of HCl that is going to neutralize the 25 centimeter cube of sodium hydroxide, and this is the equivalence point. So the equivalence point here will be at 25 centimeter cube. Of course, here we have 5, 10, 15, 20, 25, 30, 35, and so on. So we will see that the equivalence point is the volume of HCl required to neutralize the 25 centimeter cube of sodium hydroxide, and it should be 25 because we are using the same concentrations, and the mole ratio between HCl and sodium hydroxide is 1:1. Understand this part, or shall I repeat it? Understand why 25 centimeter cube of HCl will neutralize the 25 centimeter cube of sodium hydroxide? Time. Okay. Repeat. Okay. Yani, you know what is neutralization, isn't it, ya Sarah? Yani, if you have HCl reacting with sodium hydroxide giving sodium chloride plus water. If they told you in a problem that you are using the sodium hydroxide with concentration of 1 mole per decimeter cube, and you use 25 centimeter cube of sodium hydroxide, and also you used a concentration of HCl 1 mole per decimeter cube, and they ask you to find the volume that is going to neutralize this 25. What do? Do you remember?
Yeah, the volume is the concentration divided by moles.
What is the rule? Do you remember the rule? The number of moles equal?
Volume times concentration divided by 1,000.
Yes, excellent. So the number of moles is equal to the concentration over the volume in centimeter cube divided by 1,000, right? Excellent. So what is the first step that we usually do in mole problems?
Find the number of moles.
Excellent. Of what? Excellent. Of what?
Of sodium hydroxide first.
Excellent. Because they give you the number of moles, they give you the volume and the concentration of sodium hydroxide, so you can get the number of moles of sodium hydroxide, which is equal to the concentration times the volume. Okay, yani it doesn't matter, yani here that we divide by 1,000, I'm just showing you that it will be the same volume. And we get here 2.5 times 10 to the power minus 2, isn't it? So this is the number of moles of sodium hydroxide. So what will be the second step, if you remember?
Find the ratio, which is 1:1. So
Excellent.
The moles of
the ratio
HCl is the
1:1.
same.
So the number of moles of HCl is the same. Excellent. And then you want the volume of HCl. What do you do?
The moles divided by the concentration.
Yes, so the volume of HCl is equal to the number of moles divided by the concentration, which is 2.5 times 10 to the power minus 2 divided by the concentration, which is 1, which means 2.5 times 10 to the power minus 2 decimeter cube, or 25 centimeter cube, right? So you got the volume, 25. So instead of doing all these calculations, here, since the mole ratio is 1:1, and since the concentrations are the same, this means that the volume will also be the same. right or not?
Yeah.
Understand what I mean يا سارة ولا إيه؟
Yeah,
if
I
you have
understand. Thank you.
if you have, you're welcome, dear. So if you have the same concentration, if you have the same number of moles, so if you know the volume of one of them, it will be the same volume for the other. Okay, so in the titration curves, we are expecting here that the volume of HCl that we are going to add from the burette is the same as the volume of sodium hydroxide, since we are using the same concentrations. The HCl and the sodium hydroxide have the same concentrations. We used, and the mole ratio is 1:1, and we use 25 centimeter cube. So we are expecting from the beginning that the volume of HCl that will neutralize the sodium hydroxide is also 25 by doing our calculations, or by expecting yani from the mole ratio and what I told you now. So now I want to plot the titration curve, how to draw the titration curve. As we said that we started with sodium hydroxide, and sodium hydroxide is a strong base, which means that the pH is between 13, 14, so let it be 14, okay? Now what happens when I add HCl to the sodium hydroxide? I'm adding drops, and here only drops are added. And after I add each centimeter cube, I find out what happens to the pH. I read here in the pH meter, I read the pH of the solution. So when we add HCl to the sodium hydroxide, it will form sodium chloride. And we took the yesterday, the sodium chloride is a neutral salt. So this means that when sodium hydroxide reacts with whatever I added from the HCl, I added drops of HCl to the sodium hydroxide. Most of the solution is still in the form of sodium hydroxide because I added only drops. The drops I added from the HCl reacted with only drops of the sodium hydroxide, but the rest of the solution is still in the form of sodium hydroxide, which is the strong base. And when HCl reacted with sodium hydroxide, it formed the neutral salt, sodium chloride, as we took yesterday. Because it comes from a strong acid and a strong base, then the salt will be neutral. We took this yesterday. So this means that our solution still consists mostly of sodium hydroxide, which is a strong base, and only a small amount of sodium chloride, which is neutral and will not affect the pH of the solution. Because sodium hydroxide is a strong base, it has a pH 14. The sodium chloride formed is neutral, so it will not affect the value of the pH here. But we will see that the curve will start to decrease a little bit. It does not decrease a lot. It decreases by a small amount. Why it decreases by a small amount? It decreases by a small amount because still our solution is a strong base. Even until we add 24.9, even if you add 24.9 centimeter cube of the acid to the base, it will react with 24.9 centimeter cube of the sodium hydroxide. This will form the sodium chloride, which is neutral, but there is still a drop of sodium hydroxide that did not react, and so the pH here will also measure nearly 14. But why does it changes so little? That's because the concentration is varying, because when you add, if you have a certain solution, the number of moles does not change. But as you add another solution, this means that your initial solution started to be diluted. When it is diluted, its concentration decreases. The concentration decreases, and that's why the pH here decreases. So I'm going to give you a note here. We say that for any solution, as we add another solution to it, its number of moles does not change, but its concentration changes. The concentration changes because it is affected by the volume. The number of moles will not change. But since the volume of the solution is increasing, the concentration will decrease because there is an inverse proportionality between the concentration and the volume. The number of moles does not change. But if the volume is increasing, then the concentration is decreasing so as to get the same number of moles at the end. The number of moles of any solution does not change. But if you are adding another solution to your solution, this means that the volume of the solution is increasing. So if this increasing and for the number of moles to be the same, this means that the concentration will decrease. Understand me what I mean, or do you have a question? So we are going to see that for any solution, its number of moles remain the same all the while. But what will change will be the concentration, because as the volume changes, then the concentration will also change. So here in the previous plot, when we started with a pH equal 14, because we are using sodium hydroxide of 1 mole per decimeter cube, and then we are going to add HCl. When we add HCl, whatever drops go down to the sodium hydroxide, it will react with the sodium hydroxide to form sodium chloride and water, which is neutral. But the rest of the solution is in the form of sodium hydroxide. So the pH is also nearly 14, but it decreases because by adding more and more of HCl, the solution volume increases, which means that the concentration of sodium hydroxide will decrease. And when the concentration decreases, the pH also decreases. Understand till here, or do you have any question? Please, if you have any question, ask. Right.
Can you repeat?
Repeat from where, Yasin? From the beginning?
No, the last part that you said, because I'm lagging and I didn't hear much.
I said that here you are placing sodium hydroxide. You are placing sodium hydroxide in a beaker, right? What is the pH of sodium hydroxide, Yasin?
14.
14. So we started our plot with 14, right? Now, what happens when we add HCl to the sodium hydroxide? Will the sodium hydroxide remain as it is, or it will react with HCl?
It's going to react.
Forming what?
NaCl, sodium chloride.
Right. So sodium chloride, is its pH 14 as well as the sodium hydroxide, or it differs?
No, it's different.
What is the pH of sodium chloride?
7.
It is 7 because it is neutral, right? So this means that it will not affect the pH of sodium hydroxide. It should not affect the sodium hydroxide because you are adding to the sodium hydroxide sodium chloride that started to form here in the solution. It will not affect the pH of the rest of the solution, which is the sodium hydroxide. So as you add drops of HCl to the sodium hydroxide, then drops of sodium chloride are going to be formed, but the rest of the solution is still sodium hydroxide with a high pH, right? But what happens is that the pH decreases very, very slightly. It decreases very, very slightly. And sometimes even in some of the reference books, in Cambridge, they draw it as a straight line. But in Edexcel, you have to draw it slightly decreasing, slightly, very, very slightly decreasing. And why is it slightly decreasing the pH? Because when you add HCl to the sodium hydroxide, then the volume of the whole solution is increasing. At the beginning, it was 25. But when you added another 20 centimeter cube of HCl, this means that the volume, the total volume here will be 45. And from a moment I told you that when the volume increases, then this means that the concentration of sodium hydroxide will decrease because you are adding more and more HCl, then the volume of the whole solution increases. So the concentration of sodium hydroxide is decreasing. And when the concentration of sodium hydroxide decreases, then the pH also decreases, but very slightly. Okay,
Okay, yeah.
until,
Thank you, Miss.
you're welcome, dear. Until we add 24.9, for example, until we add 24.9 centimeter cube of HCl, what will happen? We'll see that there will be a little bit curvature here, because when you add 25 centimeter cube, the 25 centimeter cube of HCl that you are going to add completely neutralizes the 25 centimeter cube of sodium hydroxide, and this will form sodium chloride totally. The solution, all the solution now will be sodium chloride. It will be a neutral solution because all the sodium hydroxide that was present in the beaker completely reacted with the HCl, forming sodium chloride, which is a neutral solution having a pH of 7. And so you will see that there will be a sudden drop in pH. There will be a sudden drop in pH, changing. You see here it's about, the volume here is about, the volume of HCl here is about 24.9 centimeter cube. But at the 25 centimeter cube exactly, you will see that there will be a steep drop of pH from about, here it's about 11.3 till about 2.8, or you can say 3, whatever. And then afterwards, if you add more, I'm going to repeat this, after you add more of HCl, then the solution now starts to be acidic. And since HCl is a strong acid, then you will see that the curve will go down until pH equal, until the pH of equal 1 or 2 maximum, because HCl is a strong acid. I'm going to repeat this. I said that here we are drawing what we call the pH curves in order to determine which indicators are we going to use. And if you have an acid and a base and you are confused, you do not know which indicator to use, because they are not only the 2 indicators that we took in O level and AS, there are more indicators that we are going to see. So in order to determine which indicator to use, scientists started to draw the pH curves so that we can find out which indicators are available for us to use during any titration. So we started the titration of a strong acid with a strong base. So we are going to draw what we call a pH curve. Now, how do we draw this pH curve? We are going to get a beaker and place 25 centimeter cube of sodium hydroxide with concentration of 1 mole per decimeter cube. We are going to get a burette and fill it with HCl having the same concentration. We are using the same concentration to make it simple, to make it simple for us to determine what we call the equivalence point. We said that the equivalence point is the volume of HCl that completely neutralizes the sodium hydroxide that is placed here in the beaker. So we are going to connect a pH meter, and the pH meter has an electrode or a probe that we place it inside the solution of sodium hydroxide. And at once it will read here in the pH meter, it will read 14. And that's because sodium hydroxide is a strong base. And we know that strong bases have pH ranges ranging from 12 to 14. So here, because the concentration of sodium hydroxide is high, so the pH here is 14. Now, what happens as we add drops of HCl to the sodium hydroxide? Each drop that we place from the HCl to the sodium hydroxide will react with the sodium hydroxide to produce sodium chloride and water. But we are adding only drops, 1 centimeter cube, for example. If I added 1 centimeter cube, it will react with 1 centimeter cube of the sodium hydroxide. But the rest of the sodium hydroxide, which is the 24 centimeter cube, is still present in the form of sodium hydroxide, which means that the pH is nearly 14. But as we add more and more of the HCl to the sodium hydroxide, each 5 centimeter cube I'm adding in excess of HCl to the sodium hydroxide we also form sodium chloride, which is neutral, but the amount of sodium hydroxide, or the pH, will decrease a little. And that's because we said that as the volume increases, then the concentration of sodium hydroxide will decrease, because the concentration depends on the volume. So at the beginning, we started with 25, but as you added 20 centimeter cube of HCl, then the total volume in the solution will be 45, not 25, which means that the concentration must decrease so that the number of moles be the same, because the number of moles does not change. What can change is the concentration and the volume, but the number of moles of sodium hydroxide that we placed at the beginning is still the same. So here we see that the pH curve slightly decreases as more and more of HCl is added, but it does not change much. Yani, as I told you that in some books, even they draw it as a straight line. But in your book, it is a little bit yani, decreasing, because the concentration of sodium hydroxide is decreasing. Till 24.9 centimeter cube added of HCl, this means it reacted with 24.9 centimeter cube of sodium hydroxide, but there is still present 0.1 centimeter cube of sodium hydroxide that did not react. So the pH up till here is slightly turning, as you see here. But when we add exactly 25 centimeter cube, which are required to neutralize completely the 25 centimeter cube of the sodium hydroxide, you will see that there will be a steep drop in the pH. Why there is a steep drop? There is a steep drop because we have seen yesterday that the pH of sodium chloride is 7. So we'll see that the pH will drop to 7. But also, when we add the after neutralization, after the 25, if you add even 25.1 centimeter cube of HCl, it means that the 25 of HCl, these 25 reacted with the 25 of the sodium hydroxide. But there will be 0.1 centimeter cube of HCl now present in excess. After the 25 centimeter cube of HCl neutralized completely, means that they reacted completely with this 25 centimeter cube of sodium hydroxide, there will be 0.1 centimeter cube of HCl, which will affect the pH, because now the solution will be totally acidic. And this means that since HCl is a strong acid, you will see that the pH drops till pH between 0 and 2, that of the HCl. So this will be our curve. You will see that here the 7 is in between. Yani here you have to know these values. You have to know that you are going to start the steep drop from about 11. Yani let it be 11. Don't say masan. Yani if you know it, 11.3 is okay. But if you do not remember 11.3, just draw it from the steep drop from 11 to 3. From 11 to 3, and the 7 will be in the middle. Yani it should be in the middle, but of course my drawing here doesn't show it in the middle, but it should be in the middle. The 7 should be drawn in the middle. Yani this part is equal to that part. So this is the plot of the pH curve between HCl and sodium hydroxide, or any strong acid with a strong base. Understand it? Well, yani if you have any question, please ask.
Miss, I have a question.
Yes.
So, Miss, why does the curve, like, why does it keep decreasing when it's at 7? Isn't it supposed to, مثلا, like at 7 it stops and then it decreases further, like at 25.1?
This
if you get what I
is
mean.
the volume, right? This
Like,
is
why
the
is it-
volume. This is the volume of HCl you added, which is the 25. This is the volume of HCl, right? So when you added 25 centimeter cube, what happened to the solution? Didn't it all turn to sodium chloride? Right?
Yes.
So it turned to sodium chloride, and so the pH dropped, right? Now, what happens when you added only one drop in excess of HCl? Will the solution remain
It it's gonna change to an acid.
That's why the pH changed. Instead of 7, it became pH 2. It became pH 1. Okay?
Yeah,
يعني
Miss,
this
I
drop-
know, but
Hmm.
like my question is يعني why doesn't it stop at 7 بعدين decrease further at 25.1 لأنه كده it looks like it's يعني stopping at 2.8.
يعني at this point, at 24.9, it was still basic, right? And at 25.1, it turned to acidic. So what happened to the pH? يعني it dropped, the
It
pH
decreased.
dropped from a strong base to a strong
14.
acid. So that's why it passed through the 7. Understand me? يعني
Oh, okay. So
يعني
7 is not like a point where it stops.
no, it didn't stop. The pH of the solution,
Oh.
when you added exactly 25 centimeter cube of the HCl to the 25 centimeter cube of the sodium hydroxide, when you added this volume exactly to that, the pH of the solution is 7.
Mhm.
Okay?
Good.
But before this 25, by only 1 point, the solution was a base. And after this
Mhm.
point, by only 0.1, it became acidic. So to draw this, the pH will drop. It drops from the 11 to the 2 or to the 2.5 or whatever.
Oh, okay.
You understand
Thank you,
it,
Miss.
ولا إيه? You're welcome,
Yeah.
dear.
Yes,
Jack?
yes, yes.
Yes, okay. Jack, do you have a question?
Yes, doctor. Should the 11.3 be 11.2? Because I can't understand this.
You don't understand why is it 11.3?
Yeah, it's not 11.2 because
It doesn't
think
matter.
it,
Yani if you write it 11, if you write it 11.2, if you write it 11.3, it doesn't matter. But this straight line, this steep line, they told us that the steepness started from 11.13 to 2.8. If you draw it from 11, it's okay. If you draw it from 11.2, it's okay. Understand me?
Okay.
Yani they told us that the steep line starts from, if you do it in your lab, if you go to school and you can do this experiment in your lab, then when they did it in the lab, they found that this steep line was between 11.3 to 2.8. But if you draw it at 11, it's okay. If you draw it at 11.2, it's okay. But you have to draw it within this range, between 11 and 3. Okay, Jack?
Okay. Okay.
What other questions do you have? Yes. Wafa, your question, please.
Yes, Miss. Miss, why at 25 like centimeter cube, the pH drops till 3? Like why
Because
more than 25, the pH will be dropping till 3?
why more than 25? It will be 3. Wafa, I can't hear you. Would you please raise your voice?
Like I meant why.
Mm.
I said why at 25 centimeter cube, the temperature, like the pH drops till 3. Isn't
Okay,
it will be isn't it neutral at 25?
it is neutral. So what happens when it is neutral? The pH will drop to 7, right? So here at 24.9, it is still alkaline. So the pH is high, right? At 24.9. At 25.1, what happens? The solution completely turned into acidic. Right or not? So to drop from 11 to 2, then we have this steep line. There should be a complete drop. At 25 exactly, the solution is neutral, and neutral means that the pH is 7. So the pH 7 is in between, it's in the middle between this part and this part. At 24.9, it was still alkaline. At 25.1, it became acidic. So how can you draw this change? How can you draw that there was a change? It was not a gradual change. It was a drop from the pH 11.3, which is alkaline, to 2.8, which is acidic. So how can you draw this drop except if you draw a straight line passing through pH 7? Okay, وفاء ولا إيه ولا do you have another question? Or even if it is the same
No,
question.
understood. Thank you.
You understood?
Yes.
Type. Okay, you're welcome. Any questions? Type. Okay, so this is the pH curve or the titration curve between a strong acid and a strong base. Now, what happens if we titrate a weak acid with a strong base? Titration of a weak acid with a strong base. Weak acid like ethanoic acid, for example, and a strong base like sodium hydroxide. So also we are going to start with a beaker containing 25 centimeter cube of 1 mole per decimeter cube of sodium hydroxide, and we are placing a burette containing, we are placing a burette here containing ethanoic acid, also of 1 mole per decimeter cube. So here we have ethanoic acid having a concentration of 1 mole per decimeter cube of ethanoic acid. And we are also using the pH meter to measure the pH values. And this is the probe that is placed in the solution in order to determine the pH of the solution. Now here we are adding ethanoic acid to sodium hydroxide, also in the mole ratio of 1:1. So we get sodium ethanoate plus water. So also we get a salt, which is sodium ethanoate. Now, Rizma, is sodium ethanoate a neutral salt? Or is it acidic or is it basic? Yes, Rizma? I really don't hear you. Although your mic is open, but I can't hear you.
Sodium ethanoate would be a basic salt.
Excellent. Bravo, Alik. It's a basic salt. As we said yesterday, excellent, Rizma, since it is formed from the reaction between a weak acid with a strong base, then we said that whatever is strong will win. So if we are reacting a weak acid with a strong base, then the salt that is going to be formed is a base. It is also a base. Okay, now we are going to plot the same as we did. We are going to plot here pH against the volume of ethanoic acid added. And it's the same, since here we are using the same concentration of sodium hydroxide and ethanoic acid, we are using the same concentrations, and as the mole ratio is 1:1, this means that the volume of ethanoic acid required to neutralize the 25 centimeter cube of sodium hydroxide will be how much, Yaula? What will be the volume of ethanoic acid required to neutralize the 25 centimeter cube of sodium hydroxide? It will be
25 centimeter cube.
Yes, excellent. It will be also 25 centimeter cube. So if we have 5, 10, 15, 20, 25, so we are expecting the end point or the equivalence point to be here, the equivalence point. 30, 35, and so on. We are expecting the equivalence point, which is the volume of ethanoic acid that is going to neutralize the 25 centimeter cube of sodium hydroxide will also be 25 because both have the same concentration and they are reacting in the mole ratio 1:1. Now we start also with sodium hydroxide. We placed it in the beaker, which means that the pH is 14. So here is the pH 14, 7, and 0. Now we started with the pH 14. Now as ethanoic acid is added to sodium hydroxide, so the drops that we add from ethanoic acid will react with drops of, for example, if we added 5 centimeter cube of ethanoic acid, it will react with 5 centimeter cube of the sodium hydroxide, producing what? Producing sodium ethanoate, which is a base. And the rest of the solution, the 20 centimeter cube, are still present in the form of sodium hydroxide. So in the solution this time, we have sodium hydroxide and we have sodium ethanoate, and both are basic. Both of them are basic. And so we will see that the pH nearly does not change. Nearly, it does not change. Yani, although, yes, the solution is also getting dilute, but you will see that here in the previous example, when we had sodium chloride forming, when we reacted HCl with sodium hydroxide, the sodium chloride salt that was formed is neutral. So it didn't raise the pH, it didn't decrease or increase the pH. It is neutral. But what happened is that we drew the pH slightly decreasing because we said that the sodium chloride does not affect the pH, and at the same time the solution is getting diluted, and that's why the pH slightly decreased. But here we are reacting ethanoic acid with sodium hydroxide. The solution that is formed is also basic. So our solution is basic. It is a very strong base, and the salt that is formed is also basic. That's why you will see that the pH nearly does not change. Nearly it does not change. Okay, type. Now, when sodium ethanoate, when ethanoic acid is added to the sodium hydroxide drop by drop until we added 25 centimeter cube of the ethanoic acid, this means that this amount of ethanoic acid are the 25 centimeter cube are equal to the 25 centimeter cube of the sodium hydroxide, and so it will completely react with this 25 centimeter cube, and so we will form the basic salt. And then if we add 25.1 centimeter cube, then the solution will be acidic, but it will be a weak acid because ethanoic acid is a weak acid. So what we will see here is also at the 24.9, we are going to see a drop in pH. We are going to see a drop in pH at the 25 centimeter cube. But here you will see that the curve will not go down as in case of HCl. You see the steepness was too long because we are changing from pH 11 to pH 3. But when a weak acid is used, this means that the pH will reach about from 3 to 5 because a weak acid is between 3 to 5. So because we are dealing with ethanoic acid, it's a weak acid. So when we have a drop here, the drop will not go down till pH 0 or 1. It will reach only maybe till 5 because it's a weak acid that is going to be formed. And as we said yesterday, if you have a basic salt, this means that its pH will be higher than 7. And so we'll find that the end point here, or the equivalence point here, will have a pH of about 8.5 or between 8 and 9. And let this be 7. I need to show that there is a difference. So if this is the 7, So we will see that as the salt formed is not a neutral salt, as in case of HCl, it was a neutral salt. That's why we said that the pH of the neutralization is at 7. But here, because whatever is formed here is a basic salt, we will see that the equivalence point is at a pH of 8.5 because a basic salt is formed. And the curve will reach only till pH 5 because ethanoic acid is formed after the endpoint. I will repeat this. In this titration, we are titrating a weak acid like ethanoic acid with sodium hydroxide, forming the sodium ethanoate and water. So here, we started with sodium hydroxide at a pH of 14. And then we are adding ethanoic acid. As we add ethanoic acid to the sodium hydroxide solution, which is basic, another base is formed, which is the salt. This is base and this is a base, so that's why here the pH does not change as it changed in case of the reaction between HCl and sodium hydroxide, which slightly decreased. But here, nearly there is no change. As we are adding more and more of the ethanoic acid to the sodium hydroxide, until we reach 24.9 centimeter cube of the ethanoic acid, still the solution was alkaline. It was basic. And at 25.1 centimeter cube of ethanoic acid added, 25 reacted with the 25 centimeter cube of sodium hydroxide, and there is left 0.1 centimeter cube of ethanoic acid that remained in the solution in the form of an acid. But since it is a weak acid, then we will see that the pH curve will reach about pH 5. That's why the curve here, the steep line, does not go down as in case of the strong acid with a strong base. You see this steepness is too long, reaching between 0 and 1 pH. But in the weak acid, it will reach only till pH 5. And we will see that the middle here, which is the pH of the neutralization, because in neutralization, this basic salt is formed, we'll see that the pH will be 8.5 greater than 7 because the solution will be basic due to the formation of this salt. Okay, do you have any question? Any question? Right. Let us see what happens. Of course, here also I have to tell you that here the steepness here starts with the steep drop, starts from also about 11.3 or mumkin you can say 11 and end up till about 5 or 5.5. Yani from 11 to 5. From 11 to 5, so 5, 6, 7, 8, 9, 10, 11, it's 6. So from 5, 5 plus 3 makes 8, and 8 plus 3 makes 11. So the 8.5 is in between the 5 and the 11.3. Now, the third titration that we are going to go through is the titration of a strong acid, titration of a strong acid against a weak base, against a weak base. So we are going to take the strong acid as HCl, for example, it's a strong acid, and the weak base like ammonia aqueous, it is a weak base. And so we are going to place, as usual, 25 centimeter cube of ammonia, having a concentration of 1 mole per decimeter cube in the conical, in the beaker, or conical, yani it doesn't differ. And we are going to place here in the burette we are going to place HCl, which is the strong acid, having also a concentration of 1 mole per decimeter cube. And as I told you, we place them having the same concentration so that we expect the volume of neutralization to be at 25. Of course, here we are going to put the pH meter. And we connect it using its probe to the solution. Now we plot the curve. The pH against the volume of HCl added. And as we said that if we are placing here 0, 5, 10, 15, 20, 25, 30, 35, and so on, then we are expecting the equivalence point. We said equivalence point is the volume of the acid added that will completely neutralize the base placed in the beaker. Now we have ammonia. And is ammonia, Yasara, a weak or a strong base?
A strong base.
Ammonia. Sodium hydroxide, potassium hydroxide are strong bases, but ammonia is? Yes, yes, sir. Ammonia is?
A weak base.
Yes, excellent. It's a weak base. Ammonia is a weak base. Sodium hydroxide and potassium hydroxide are strong bases, but ammonia is a weak base. And when we have a weak base, Yasamia, what will be the pH? Around what, yeah? Yes, excellent, yes, Samia. So Samia
Miss,
said
did you see my name?
Excuse me, Sarah?
No,
Yes.
sorry, Miss. I thought you said my name.
No, I said Samia. Okay, thank you. Thank you, Sarah. Yes, excellent, Samia. The pH should be between 9 and 11. Whenever we have a weak base, the pH would be between 9 and 11. Strong base between 12 and 14. As we said here, the strong base is between 12 and 14. You see, the strong base, like sodium hydroxide or potassium hydroxide, it is between 12 and 14. But if you have a weak base, then the pH is around from 9 to 11. So if we start at 11, if this is 11, of course, here we have 12, 13, 14. So we are going to start by 11. I'm saying all this because all this you are going to be asked to draw. Yani they are going to ask you to draw pH titration curves. So you have to know from where are you going to start. And of course, afterwards, we are also going to see that sometimes we are going to do calculations in order to get exactly the value, not to say between 9 and 11. We have to know exactly from where and we put it on the plot. Now, yani, take it step by step. So we are starting with a pH of 11 because ammonia is a weak base. Now, what happens when ammonia reacts with HCl? What will it form? What will it form, ya Mu'taman? When ammonia reacts
Ammonium
with
chloride.
Excellent. It will form ammonium chloride. And of course, because this is aqueous, so it will form water. Yes, excellent. Now, Mu'taman, yesterday, what did we say about ammonium chloride? It is a salt, but is it an acidic salt, an alkaline salt, or a neutral salt?
Acidic.
Bravo, excellent. It is an acidic salt because it comes from a weak base and a strong acid. And we said that if we have something strong, it is the one that is going to win. So if I have weak base reacting with a strong acid, it will form an acidic salt. So we are expecting the value of the salt that is going to be formed at the equivalence point to be acidic. It means that its pH should be less than 7. That's what we are expecting. Type. So now, what will be the curve that we are going to draw? We started with ammonia. Now, when we added HCl to the ammonia and it formed an acidic salt, So will the pH remain the same as it did in case of sodium hydroxide and ammonia? I'm going to repeat. Here, when we added sodium hydroxide to HCl and a neutral salt was formed, the pH remained nearly the same. In the second one, when we added a weak acid to a base and the salt formed was basic, so we said that because the salt formed is base and the solution itself is a base, so both of them are basic. That's why the pH also almost remained the same. But in that case, we are adding HCl to ammonia. It formed an acidic salt. So I started with a base, but the salt that is formed is acidic. So what will happen to the curve? We'll see that at the beginning, we will see that there will be a drop in pH. You see? Yani I didn't draw the pH curve like this, like when we did in the previous two cases. No, there was a drop in pH, and that's because the salt form is now acidic. You have a weak base, and now the salt that is formed is acidic, and this will cause a drop in the pH, after which the pH will remain almost changing يعني very slightly. So there was a drop at the beginning, and then the curve is changing or decreasing slightly as we usually do until we reach the 25 volume. We'll see that there will be a drop in pH, and this drop will go down because whatever is going يعني after the 25 centimeter cube, the solution will be strongly acidic due to the presence of HCl, and that's why the pH will drop till about between 0 and 1. So there will be a drop here. يعني here we can draw it in this way. There is a drop in the pH. There is a drop in the pH, and the salt that is formed is an acid salt, and that's why we will see that the pH of the neutralization will be about 5.5, and we will see that the steep line يعني nearly starts from 8 and end up with about 3. So here we have from 8 to 3, we have 5. So this is 2.5, and then another 2.5. So you will see that this part is equal to that part, and here is equal to that part. But the pH at which the neutralization will take place will be at a pH of 5.5, because the solution formed here will be acidic due to the formation of the ammonium chloride. So here there will be a drop in pH. It will not stay the same as the previous two cases. It will not stay nearly the same. And here there is nearly the same. The other one was decreasing slightly. But in case of ammonia with HCl, we will see that there is a drop in the pH. Why there will be a drop? Because the salt formed is acidic. So if you have a weak base in the solution and an acidic salt is also formed, this will affect the pH of ammonia. It will decrease because an acid is now present with it. So there will be a drop and then small change, very small change, until we reach at about 24.9, the solution is still alkaline. At 25.1, it will be strongly acidic, and that's why there will be a drop in pH from about 8 to about 3, and we'll see that the middle is the pH of the salt that is formed in the neutralization. It will have a pH of 5.5. So this is called the equivalence point. We call this the equivalence. The equivalence point is this point. It is the 25. And this is the pH of the equivalence point. How at the equivalence point. The pH at the equivalence point. Okay, do you all understand? Well, if you have any question, please ask me. Type. What if you have a titration? Yes. Repeat this one. We said that if you have, when the equivalence point is, this is the equivalence point, which is the 25. What is the equivalence point? It is the volume of HCl that is required to completely neutralize the 25 centimeter cube of ammonia. This is the 25. This is the equivalence point. But this is the pH at the equivalence point. It means when you reach the equivalence point where all the ammonia reacted with the HCl, then we said that this is called the equivalence point. When you measure the pH, it's going to be 5.5. It's not going to be 7 because now there is an acidic salt present in the solution. And this is also in all the previous curves. And here, this is the equivalence point. This is the equivalence point. And this is the pH at the equivalence point because the solution now is basic. A basic salt is formed. Okay, thank you so much. Type. What if we have titration between a weak acid and a weak base? A weak acid with a weak base. Like, for example, ethanoic acid with a weak base like ammonia. So we have a titration of a weak acid with a weak base. We also place the weak base in the beaker or conical flask, and we add the acid from the burette. And then we want to plot the curve between the pH and the volume added of the acid. And since also we are using 25 centimeter cube of 1 mole per decimeter cube of ammonia, and we are using ethanoic acid having a concentration of 1 mole per decimeter cube of ethanoic acid, then we are expecting that the equivalence point to be at 25. Now, we started with ammonia and we said that ammonia is a weak base, so the pH that we are going to start is between 9 and 11. So we are going to start with a pH of 11. And then when we add the acid, then we will see also that here بقى, يعني you will see something that is different, that the curve is going to يعني be like that. And there will be only, there will be only what we call an inflection point. There will be no steepness here. There will be only an inflection point. Inflection point means changing from something to another thing. But here we are starting with a weak base and ending with a weak acid. There will be no steep line here. There will be only an inflection point which corresponds to the corresponding to the pH of the equivalence point. And if you remember yesterday, we said that when you are having a weak acid with a weak base, the salt that is formed, let me write the equation. You are reacting ethanoic acid with ammonia, aqueous. So the salt formed is called ammonium ethanoate plus water. And we said that here, the salt here will be neutral, just like, because here you have a weak acid and here you have a weak base. So neither of them will win. Neither of them will win. And so the salt formed here will be neutral. And so you will see that the inflection point here is at a pH of 7, but there is no steepness. There is no steepness in the curve because it changed from something weak to another thing that is weak. So there was no steep part. There is no steep drop in the pH. Okay, because you are changing from something weak to another thing that is weak, from a weak base to a weak acid. And so there was no steep drop in the pH. And here we say that it forms what we call an inflection point corresponding to the pH at the equivalence point. Okay, so these are the 4 titration curves that we have to know about. Of course, we are going to use these titrations, we are going to use these pH curves in order to determine which indicators we are going to use. But before I go to indicators, please, if you have any question, if you have any confusion, please ask about these 4 titration curves that I just explained. Right. Okay. Now,
Miss, can you repeat the inflection point part?
Here you are using a weak base, right? Which is ammonia. And you are adding to it a weak acid, right?
Yeah.
So what will happen? The pH will change because now it will form a neutral salt. So you will see that it goes to the neutrality, but after the neutrality at once, there will be a weak acid formed. So the curve will not go down. There will be no drop in pH. You will see that it changes from a weak base to a weak acid. The weak base will be between 9 and 11, and it changes to a weak acid between around 5. So it changes from about 9 to 7, from about 9 or 8 to 5. So there will be no drop in pH. You will see that there is only an inflection point. It means a change, a direct change from a base to an acid, but there is no a drop in pH.
Yeah,
okay,
I get it. Yes, thank you.
You're welcome. Now, we have to talk about the indicators in order afterwards to know which indicators are we going to use. So now, what are indicators? We say that indicators are weak acids or weak bases that have different colors in acids and bases, having different colors in acids and bases. Now, a weak acid, we know that a weak acid, and if we say that this is the formula of the indicator in general, if we take it as a weak acid, because most of them are weak acids. So if we start with the HIN, which is the indicator, which is in the form of a weak acid, and we know that acids are proton donors, it means that it should contain a proton. So we know that weak acids partially ionizes. Yes, of course, yes, Sarah. So the indicator HIN partially ionizes to form H positive plus IN negative. So since the indicator, this is the indicator, as it is a weak acid, then it partially ionizes. We know that acids are proton donors, so it will give a proton plus IN negative, and so it ionizes to give H positive plus IN negative. This is the acidic form of the indicator, and this is its conjugate base. We say if you take, for example, something like methyl orange, its acidic form is red in color, and its basic form is yellow in color. If we take something like methyl orange, you will see that its acidic form is red, and its alkaline form is, its conjugate base is yellow. So if it is placed in an acid, what will happen? What will happen, يا وفاء, if it is placed in an acid? And there is equilibrium.
It will be red.
It will be red because the equilibrium will shift where? Since we have here an H positive and
It
here
will
an
shift-
H positive, so the
The-
equilibrium position will shift to the left-hand side towards the formation of the red color. And that's why when we place methyl orange in an acid, it turns red. Because the acid, we have an acid, you place the indicator in, and the indicator itself has an H positive, which means that now the amount of H positive is high, so the equilibrium will shift to the left-hand side towards the red color. That's why methyl orange appears red. Type Zulfa, if we place it in an alkaline medium, what will happen? This is the indicator's equation. It's present at equilibrium. So if we place an alkaline, yes, excellent, it will turn yellow, as Zulfa said, because now the H positive is going to react with the OH minus, and this means it will form water. And so the amount of hydrogen ion decreases in the equilibrium position, and so the position of equilibrium will shift to the right-hand side to compensate for the loss of the hydrogen ions that reacted with these. And so the reaction will shift, the equilibrium position shifts to the right-hand side towards the yellow color. That's why when we have methyl orange in the acid medium, it is red, and in the alkaline medium, it is yellow. This is when the concentration of HCN increased, HIN increased, and the concentration of IN negative increased. But there is a point, which is the end point. We said that we have an end point. So at the end point, we have here HIN present at equilibrium with H positive plus IN negative. So at the end point, we'll see that the concentration of the HIN is equal to the concentration of the IN negative. And since we have here equilibrium, we have an equilibrium constant, which we are going to call it the equilibrium constant of the indicator. As we studied, that the equilibrium constant is equal to the concentration of the hydrogen ion times the concentration of the IN negative divided by the concentration of the HIN. And since we said that at the end point, the concentration of both species are equal at the end point, which means that these are going to be canceled. So we'll see that the hydrogen ion concentration is equal to the equilibrium constant of the indicator, which has a value of course, it is given 2 × 10⁻⁻⁴ mole per decimeter cube. And so from here, the pH, which is equal to minus log the 2 × 10⁻⁻⁴, is equal to 3.7. So at pH equal 3.7, methyl orange change its color to the orange color. I will repeat this. We know that methyl orange has a yellow color in the alkaline medium and has a red color in the acidic medium. That's because methyl orange is a weak acid and it ionizes to give H positive plus IN negative. Okay, so if it is placed in an acid medium, the hydrogen ion concentration increases, and this means that the equilibrium will shift towards the left-hand side, towards the formation of more HIN, which has the red color, and that's why methyl orange appears red. In alkaline medium, the OH ion will react with the H positive forming water, so there will be a loss in the amount of H positive in the equilibrium, and so the equilibrium position shifts to the right-hand side to produce more H positive, and so it moves towards the formation of more IN negative, which has a yellow color. Now, we said that we have to choose our indicator. So to choose our indicator, we have to know at which pH it will change its color. We have to know at which pH it will change its color. So we said that HIN gives H positive plus IN negative. And since there is an equilibrium, there should be an equilibrium constant that we are going to call it K indicator. At a certain point, the concentration of both the HIN is equal to the IN, which means that if we substitute here in the expression of the K indicator, it is equal to the concentration of H positive times the concentration of IN negative over the concentration of HIN. So when both are equal, then they are canceled together. And this means that the concentration of H positive is equal to the K indicator, which is 2 times 10 to the power minus 4 for methyl orange. And when we take the pH, which is minus log this value, it will be 3.7, which means that methyl orange will have an orange color at exactly pH equal 3.7. If the pH of a solution is 3.7, then it will change its color to be the orange color. But we want to know at which pH it will be red and at which pH it will be yellow. It should be red at when we place it in an acid medium. It means that the concentration, when the concentration of the acid species is equal to 10 times the indicator concentration, indicator negative concentration, then the indicator will have the red color corresponding to the acid medium. We said that K indicator is equal to the concentration of H positive times IN negative over HIN. So we said that if we have the HIN concentration equal to the IN negative concentration, they will cancel, and the pH at which the methyl orange will change its color to the orange color will be at exactly a pH of 3.7. Now, when it is in the acid medium, it is red. And when we have an acid medium is when the concentration of the hydrogen of the HIN is equal to 10 times, we are taking the extreme case where it is equal to 10 times the IN. So this means that the K indicator will be equal to, I'm going to place the H positive as it is and the IN negative as it is, but instead of HIN, I'm going to place 10 concentration of indicator minus. So these can cancel, from which, and of course the K indicator, we knew it from before that it is 2 times 10 to the power minus 4. I think it was like this. And from which we say that the H positive is equal to 10 times 2 times 10 to the power minus 4, which is 2 times 10 to the power minus 3, from which we get the pH to be equal to about 2.7, I think. So at this pH, the color of the indicator is going to be the color of methyl orange is going to be red. We are seeing at which pH the color of the indicator, the methyl orange, we are dealing now with the methyl orange, will be red, and when it will it be yellow, and when it is orange. It is orange when the concentration of the HIN and IN are equal. And so the pH will be 3.7. And it is red if the concentration of HIN is 10 times the concentration of the IN negative. So by substitution, we found that the pH is equal to 2.7. And it is yellow when the concentration of IN negative is 10 times the concentration of the HIN. So the KIN is equal to H positive. We are going to remove the IN negative and replace 10 times the concentration of HIN divided by the concentration of HIN. And so the HIN cancel, and from which we find that H positive equal 2 times 10 to the power minus 4 divided by 10, which is 2 times 10 to the power minus 5. And so we will find that the pH here will be equal to 4.7. So by this way, we calculated the value of pH at which the indicator is neutral, has the neutral color. We calculated the pH at which it will have the color in the acid medium, and we calculated the pH at which the indicator had a color in the alkaline medium. And so from these calculations, and of course they are going to do the same for all the indicators, so we will get a table here that you are going to get in your questions or in the data booklet. You see this table. This table shows you that methyl orange, as we said, it exactly changed its color at a pH of 3.7, which is its pK indicator. But it has a range. Yani the 3.7 will lie within the range. Yani before 3.1, the methyl orange will have its acidic color, which is red. And after the 4.4, after the pH 4.4, it will have a yellow color. And the orange color will be at a pH between 3.1 to 4.4. If you subtract this, dividing by 2, it will be 3.7. Of course, you are not going to memorize this table at all. Of course, they are going to bring you. I'm going to show you that, inshallah, next time you will see that this is very simple. But because you are hearing it for the first time, maybe it is very complicated for you. But you will see that next time when we do the titration curves next time, I'm going to revise them back. And then we will see how do we choose the indicators. Each indicator has a pH range. We are not going to look at this. We are going to look at the pH range at which they change their color to the intermediate color. So methyl orange changed its color between 3.1 to 4.4. What do I mean by that? This is its endpoint. It means that before the 3.1, it will have the red color in the acid medium. After the 4.4, it will have the yellow color of the IN negative, its negative species. The bromophenol blue, this is another indicator that you didn't hear of before. Bromophenol blue has a pH range between 2.8 to 4.6. It means that before the 2.8, before the pH 2.8, it has a yellow color, and after that, it will have a blue color, and the middle color will be in between the 2.8 to 4.6. So we say that it changed its color at the pH range from 2.8 to 4.6. There is another indicator called bromothiamyl blue. It changed its color in the pH range between 6 and 7.6. Its color in the acid medium is yellow. Its color in the alkaline medium is blue. The phenol red changed its color in a pH range between 6.8 to 8.4. Its color in the acid medium is yellow, its color in the alkaline medium is red, and the phenolphthalein changed its color in the range between 8 and 10. It is colorless in the acid medium and red in the alkaline medium. They are going to give you a table like this in the exam paper. And inshallah, because I know that you are very exhausted now, I'm going to end the lesson now. So we are going to see how, using this table, we can choose the indicator that we will use in any titration curve that they bring us. They can bring you other indicators as well, alizarin yellow or whatever. Yani there are a lot of indicators, they can give it to you. As long as they give you the pH range at which the indicator changed its color and what is its color in the acid medium and what is its color in the alkaline medium, we can solve whatever they are asking us. Now, I want to show you once more the curves that we took today. And if you have any question, this is the pH curve of a strong acid with a strong base. You see that it changed gradually until the volume of 25. There was a sharp drop, after which there was a change in pH to be between 0 and 1. If you have a strong base with a weak acid, then it started also the pH at 14, and then there was a sharp drop until we reached, because there was a weak acid, the pH ranged until about 4. Here we have a weak base with a strong acid, so there was a drop in pH and then gradual change and then the steep line, and then the pH dropped to 0 or between 0 and 1. If you have weak and weak, you get only an inflection point. Please revise this. And yani, it's not my choice not to solve classified questions now, because you will see that when we solve the classified questions, you will see that it will include everything. So yani, it includes even the part that comes after that. That's why yani, I have no choice, because if we start to solve any classified question, you will see that they are asking about whatever we didn't take yet. That's why I have to give you the complete lesson, and then we can solve the classified. Okay. Okay, thank you so much. If you have any question, I have time. And if you have any question, you could ask me and I will answer. Right. Okay. Thank you so much. See you inshallah on Tuesday. Bye-bye.
Thank you, Miss. Have a nice